This video is on temperature and rate. We'll be using a note packet that looks something like this. So some of this stuff we've already talked about. It'll be a review, but it's worth restating, of course. So I think most of us know that the rate of most reactions increase as temperature increases. Okay, it's kind of a common sense thing. We talked about that at the very beginning of this chapter, a temperature being a factor that affects the rate. But the question of why becomes kind of an important question, and it's actually just because the rate constant increases with temperature too. Okay, so why does the reaction get faster as temperature increases? And the answer really is because the rate constant increases. So over in the corner there's a graph of the rate constant versus temperature, and you can see that as temperature increases, so does the rate constant. Okay, so the next heading on your paper says the collision model. And so this is kind of a conceptual topic, but we talk about the fact that reactions happen when molecules are able to collide successfully. Okay, and so we have a reaction when a reactant molecule and another reactant molecule collide together and produce a successful collision. So if we can increase the number of collisions, we can get a faster reaction. Okay, so if we can increase the number of collisions that are happening, we can get a faster reaction. And how do we normally do that? A very easy example is by increasing temperature, and that's because an increase in temp gives me an increase in kinetic energy. Okay, which means my molecules are now moving faster. They collide more frequently, so I now have more collisions. Which of course means I have a faster reaction. And so this can all be taken the other way too, saying that if we decrease temp, we decrease kinetic energy, we decrease the number of collisions, and therefore we decrease the rate of our reaction. But there's an important kind of point here that it says, but not all collisions are successful. Okay, or not all collisions between reactant molecules produce a product molecule. And so the answer is why. There has to be something else that governs collisions other than the fact that they just have to collide together. Okay, and that factor is the orientation. And so this is kind of a hard thing to talk about on a video, but I will do my best. Okay, so in addition to having, to colliding, the molecules have to have a correct orientation. You can almost think about this kind of like puzzle pieces. I probably should have found some puzzle pieces. That would have been a really good, visual to show you. But, if you think about two puzzle pieces that fit together, let's just do something that's like kind of silly. One that has like a triangular cutout and another one that has a triangular piece. I don't know. Okay, so if those two, molecules were able to collide, boom, just like this, right? The way their orientation is, it's not gonna equal a successful collision because the orientation is wrong. Okay, versus, and I'm sure you know where I'm going with this, versus if this was kind of rotated and it was flipped more like this, and then we brought them together. Right, then we have this, new puzzle piece, for example, that fits together and it produces a new product, and so that would be a successful collision. Where this is often encountered, is in a discussion of biology or biochem, and that's when we talk about enzymes. and how enzymes work. If you look up anything on enzymes, you often see them described as puzzle pieces and having to fit together properly. And so there's a idea that if molecules don't align themselves correctly, then they're not going to produce a product. So it's a little bit different. You may not have thought of that before, but that's definitely a requirement for a successful reaction. And then kind of the second requirement is having enough activation energy. And we have talked about this, but it's absolutely worth talking about again. So the main takeaway point is that molecules must possess, let's do this, must collide with a minimum energy to produce a successful collision. And that minimum energy needed is called activation energy. Gets the symbol big E, little a. So sometimes we have a situation where we have two molecules and they collide, and their orientation might be correct. Their puzzle piece might be fitting together, so to speak. But if they don't have this minimum amount of energy, they kind of just bounce off of each other. And they don't overcome that barrier to form a product. So how can I summarize that? Well, let's do this. Let's do activation energy. Is the minimum energy needed to initiate a reaction. It varies from reaction to reaction. Okay, I don't want you to think there's some magic number that that governs all. That governs all reactions. It varies. It depends on the reaction that we're talking about. But there's a minimum energy for every reaction, and that's called activation energy. Most of the time, we see it represented in graphical form, and that's what you're used to seeing, which is like an energy profile. And this would be, time. And maybe we have a reaction that looks like this. Okay. Where, at time 0, these are my reactants. At time something other than 0, as time has progressed, these would be my products, and the reaction is moving like this. Okay. Activation energy is from the reactant energy mark. It's a little high, I guess, right over here. From the reactants to the top of the hill. Okay, that's activation energy. And then, of course, this value from reactants to products, that's delta H, or enthalpy, right? So, in this case, this is an exothermic reaction, right, because energy was released. And this is my activation energy, whatever number that would be. We have learned, I believe, that the very top of this hill is called, it's got two names, called transition state. It's also called an activated complex. And that's kind of where the two reactants have collided and are almost stuck together for that instant in time before a lot of energy is released and they turn into products. Okay, so let's make a huge takeaway here. Oops. Let's say activation energy determines speed of a reaction. Okay, so what does this mean? Well, this means that a reaction that has a really big activation energy, a really tall hill to climb, is going to be a slow reaction versus a reaction that has a small activation energy, which is going to be a quick reaction. So we've also learned that we can lower the activation energy and raise the activation energy And we can lower it by adding something called a catalyst. Right, catalysts lower activation energy, and then therefore speed up reactions. We also know there's kind of an opposite to a catalyst, which raises activation energy. That's called an inhibitor. So adding a catalyst or an inhibitor will change my activation energy and will change the speed of the reaction, but will not change delta H. So you notice my reactants and my products didn't move their position. Delta H remains unchanged. And delta H has no bearing, none, on the speed of a reaction. Okay, delta H, enthalpy, or energy has nothing to do with how quickly your reaction happens. That's all activation energy. All right. So let's keep going in this packet. On the next page, it says your heading is the Arrhenius equation. So we're going to get back into graphical interpretations of kinetics. Sorry. And so there was a scientist by the name of Arrhenius, and he developed an equation that looks like this. And some of these things you're unfamiliar with, okay, is of course the rate constant. This is activation energy. This is temp in Kelvin. This is the gas constant. Been a long time since we've talked about the gas constant. And this one actually, I believe, is in, it's 8.31 units of joules per Kelvin mole. And A is a constant, okay? And we're really not going to get into what A is. I believe it's called I shouldn't use brackets, that might confuse you. I just will leave it like that. It's some kind of constant, and it's really not important to our discussion because in just a minute we're going to rearrange this equation and talk about it graphically, and we'll never really mention what A is. So it's not super important for us. So we'll actually come back to this equation in just a minute. But first I want to talk about this practice problem that you have on your packet. And I think you're missing... Oh, I'm not sure. I think your graphs are there. I don't know. If your graphs aren't there, you can draw them in. If they are there, then just bear with me as I draw them. So we have 3 graphs. Let's see. One looks like this. This is... What's it say? This is 15 kilojoules per mole, and this is negative 10. This is 25, and this is negative 15. And then I have one that looks like let's see, hold on. They're showing me that from here to here, the whole thing is 20, and from here to here, it's 5. Okay, so it says, assuming that all 3 reactions have nearly the same frequency factors, rank the following from slowest to fastest. And so the takeaway here should be the only thing that determines speed is activation energy. So we have to look at activation energy. And what are we doing? Slow to fast. Okay, so we need to look at activation energy. So in the first graph, well, let me label these, graph 1, graph 2, graph 3. In the first graph, the activation energy is fairly clearly given to you at 15, right? From the top of the hill to where the reactants were. So activation energy is 15 here. Activation energy here is 25. And this one's a little bit tricky because you might say activation energy is 20, but that's not the activation energy. Or no, I'm sorry. It is the activation energy. Sorry, I misspoke. I was thinking about the next question. So in this case, the activation energy is 20 from the reactants to the top of the hill. Okay, so I have my 3. They're all different. So my slowest reaction is going to be the one that has the tallest hill to climb, the biggest ionization energy. I just said ionization. Biggest activation energy. My gosh. So slow to fast would be reaction 2, has the biggest activation, followed by reaction 3, and then followed by reaction 1, who has the smallest activation energy and will thus be the fastest reaction. Okay? In my second problem, this is what I was thinking about when I just misspoke, says imagine that the 3 reactions are reversed. Rank them from slow to fast. Okay, different ball game. So if I'm going backwards, then my activation energy, and I'll call it EA of reverse, my activation energy would now be from what are my reactants on this side to the top of the hill. Okay, so my activation in this reaction is going to be the 10 plus the 20, plus the 15, giving me an activation energy of 25. Because see, these are now my reactants if I'm going in reverse. So for this reaction, EA of the reverse is 25 and 15. Woo! That's a huge hill. 40. And in this reaction, this is what I was thinking before, EA of the reverse is now only from here to here, which is 15, since this is 5 and the whole thing is 20. So, slowest to fastest, slowest, biggest ionization energy, absolutely, reaction 2, followed by reaction 1 with an activation of 25, followed by reaction 3 in the reverse with an activation of 15. So, very good question. That's something that I could see them asking on an AP test. Okay, and very last section, and this is where the graphical analysis comes into play. So it says determining activation energy. Okay, so we just saw this. I should make that a cursive K. Whatever. This equation just a second ago. And if we take the natural log of both sides, okay, and this is all in your textbook, it talks about how to do this, and this is math and whatever. Not worried about it, I just want you to see this. If you take the natural log of both sides, you end up with this. Okay. Which is conveniently in slope-intercept form. Okay. Where y would be the natural log of the rate constant. M would be activation energy, or the negative activation energy, over R. X would be 1 over temperature. And B would be, the y-intercept would be the natural log of that constant called A. So if I were to graph this, okay, your y would be the natural log of your rate constant. Your x-axis would be 1 over temperature. And you would get a linear relationship. And the slope would be equal to negative activation energy over R. Remember, R is a constant. We always know it. So if you were to do this and plot this information in Excel, you could generate a graph, find a slope, you know R, and you could calculate an activation energy. And I believe there's a problem that we'll encounter later that kind of tests our ability to do that.